Hello and welcome to the MIT SDM Systems Thinking webinar series. My name is Lois Slavin. I'm SDM's Communications Director and convener of the series, and I will be your host for today. Before we start, I would just like to tell you a little bit about MIT's System Design and Management program. It's a master's program for mid-career professionals, which is offered jointly by the MIT Sloan School of Management and the MIT School of Engineering. SDM provides an education that focuses on integrating the technical, business, and socio-political components of complex challenges using systems thinking. Graduates earn a master's in engineering and management from MIT. The Systems Thinking webinar series features research and real-life experience by SDM faculty, alumni, students, and industry partners. Again, the series is designed to disseminate information on how to apply systems thinking to address complex challenges in virtually any domain. Some of you may say, well, I'm not in the same industry as Amadeus, but the concepts apply no matter what domain you're in. You can find recordings from prior SDM webinars, and which can be viewed on demand at sdm.mit.edu. Within a week of today's webinar, you'll be sent a link to the recording and slides, along with speakers' contact information. And speaking of the speakers, today's speakers are Rashesh Jetty, head of R&D at Amadeus, and Martin Juvenot, who also works at Amadeus. His title is Software Architect, and he's an incoming SDM Fellow. They're going to discuss their work with Dr. Dan Sturtevant, who's an SDM alumnus and CEO of Silverthread. They will be speaking on designing software platforms for innovation and profitability. If you have any questions for the presenter at any time, please type them directly into the chat window. They will be read aloud during the Q&A session. And with that, I'll turn it over to our speakers.
Thank you, Lois. My name is Rashesh Jetty. I am the head of R&D for Americas at Amadeus. And over the next few minutes, we'll give you a quick introduction into Amadeus, our business, the complexity and the technological challenges that we face in the business that we run, and discuss two specific pilot projects that Martin on our team has been engaged in with Dan and the Silverthread team, and give you a perspective into how we've looked at software modularity and how we've looked at data-driven decision-making for some of our technology initiatives. So very quickly, Amadeus is a 30-year-old company. We were founded in 1987 by a consortium of 4 European airlines. We are celebrating our 30th birthday this year. We are headquartered in Madrid in Spain. And to give you an idea of the scale at which we operate, we do business in 195 countries, which is almost all the countries in the world. Our team is almost 15,000 people strong at this point. And last year, we generated close to 4.5 billion euros in revenue. We're also listed among the world's top 10 software companies in the world. And this is the Forbes ranking from last year. We were also on the same list the year before that. And we are one of only 2 companies outside the United States to be on this list. What is it that we do? Well, we work with some of the biggest names in travel here in North America for sure, but frankly, around the world. Our customers are airlines, travel agencies, hotel companies, rail operators, airlines, airports, ground handlers, tour operators, cruise companies, insurance providers to the travel business, and so on. We distribute airline inventory from over 700 airlines worldwide. And this inventory is available to book travel by over 90,000 travel agencies. These include corporate travel agencies, these include leisure travel agencies, and include some of the best known names in online travel and meta search. Through our platform, a travel distribution platform, we make available inventory from those 700 plus airlines, as well as over 500,000 hotel rooms and rental cars and rail, etc. We also have an IT solutions business where we build specific solutions to the same providers in travel. We have a set of departure control, flight management, and customer management solutions for airlines, of which we have over 170 airlines that trust Amadeus to provide some of these critical systems. We have reservation systems for the hotel business. We have payment solutions for the travel industry. And all of this is essentially supported by a very strong investment in research and development. We are the leading provider of technology to the travel industry. We have 20 research and development centers worldwide, and we continuously invest in research and development. We are recognized by the European Union as one of the largest R&D providers and contributors in Europe and in our industry, and we've invested over 4 billion euros over the last 10 years. To give you an idea of the complexity and the scale at which we operate, it may be useful to do a very quick flyby through the history of the last 30 years and how our systems have been built and how we operate today. So when we got started in 1987, as with a lot of companies that had to operate in a mission-critical, high-scale environment, a lot of our core platforms were built using mainframe computers. With the advent of the desktop computer, we built client-server software on top of these core systems to allow for easy access to a variety of the users that we had. With the advent of the internet, we introduced our first set of application programming interfaces, or APIs, to allow the very, very nascent but fast-growing online travel community to be able to perform the same functions that were up until that point performed mostly by dedicated and specialized travel agents with specialized equipment. And then about 10 years ago, when the iPhone entered our lives, as Steve Jobs said, it really did change everything. What that meant is all of us as consumers had access to information at our fingertips wherever we were. And what we saw, along with several of you in the industry, I'm sure, is an explosion in the volume of traffic that we were handling. Anytime any of us had a spare moment or two, we would take our phones out and check the right flight or the deals for the hotels for our next vacation. And what that has meant is over the last 10 years, we have seen the quantity of traffic that we handle go up by more than 10 times. In fact, some of our subsystems that look at flight availability have seen up to 100 times extra volume just to keep up with some of the basic transactions that the travel industry comes to rely on. And fast forward to where we are today and the world we live in, drones are real, robotics are making an increasing presence outside of the factory shop floor and into our day-to-day lives. We all work with a variety of devices, not just dedicated PCs or a mobile phone, but with tablets and laptop computers, and we are always connected. And to keep up in this landscape and to maintain our technology leadership in travel, we've had to continually look at ways in which we can improve the agility of the systems that we offer, the agility to make changes in those systems, and the ability to react and respond to the fast-moving travel industry itself. We've also begun a very deliberate and conscious effort to move away from closed proprietary systems that we got started on 30 years ago. And we've done an excellent job of actually decommissioning our entire mainframe ecosystem. Most of our platforms are now running on open systems. And over the last couple of years, we have made active investments into cloud enabling all of our technology. And in doing projects of this scale, it is very important to have a set of objective and data-driven criteria for our technology investments. And that really is the gist of the rest of this webinar. And I'll turn this over to Martin and later on to Dan, who will walk you through the initiatives that we've done together here over the last several months to look at how we can examine the modularity in software, how we can look at platforms in our software landscape, and how we can make more data-driven decisions so that we are able to fully leverage the advances in technology and serve our customers and industry in the best way possible. So with that, over to you, Martin.
All right, so the challenges we face, and as Rashesh said, we want to improve on agility. We want to make sure that we're actually building platforms that can enable us to, let's say, have richer content, develop product faster, etc. Thing is, when we exploded our mainframe into a service-oriented architecture, we created something over 5,000 services. And those services, they work under a lot of stress. We, in average, get something around 145,000 queries per second. Although we're impacting a lot of people, we are performing 2 million bookings every day. We're boarding more than 2,600 passengers. So we need to find a rather scientific approach to the way we want to invest on the platform, the way we want to conduct refactoring, the way we want to deal with eventual technical debt. And this is the project that were started with Dan, and I'm going to turn it over to you.
Sure. Yeah, so one of the things these guys have been talking about is 30 years of history developing software on all variety of devices as the history of the computer has evolved. But the software is now developed by many thousands, 5,000 or 6,000 people currently. And the thing about software, unlike many of the other things that humans have figured out to create, is that if you do it right, every single piece of software is different. Every single piece of software is different. It's unique. If it's not, then you haven't achieved reuse. So it's one of the most complex things we've ever figured out how to make, just because of the sheer volume of sort of voices in the conversation that are all interconnected in ways that people may not be able to appreciate or understand. A useful metaphor is that software development is community poetry writing at massive scale. Another challenge that the software industry faces is that these code bases, they grow over time, right? If you look at Google as an example of a company that might be at similar scale here, their 25,000 engineers commit 15 million lines of code a day. That's the equivalent of writing Linux, the Linux operating system, every single day. And the other challenge is that most of this code never dies, right? It becomes legacy code. There are many more lines of code committed every day than there are lines of code deleted. So over the decades, these bodies of code will grow and grow and grow. Maybe a century from now, it'll be something that we couldn't even fathom. But it's extremely hard for developers to keep up with the understanding that they need to have within these complex systems. There's a third challenge that Amadeus faces.
Yeah, so pretty much this is the challenge I think a lot of companies face, is that you have short-term objective and long-term objective, and this is especially true if you try to work on a software platform. So on one side, for your short-term objectives, you need to enhance existing solution. You need to build new products. You need to sign new contract. You need to grow. You need to do all those kind of things that are going to make your shareholders happy. But on the other hand, you need to invest on your platform and basically the means that are going to enable you to do that in the first place. And I mean, finding the right balance between those two objectives can be sometimes a little bit hard, and this is where then Server-Thread are helping us.
So, let's think about some of the other challenges in software, especially large-scale software. This is a picture of the Apollo 11 lander, and then also a picture of the software that was written to control it. Right. So, when we think about the large electromechanical systems that we create, or the large structures that we create as human beings, 60% of the human brain mass evolved to process three-dimensional information so that we can see it, so we can understand it, so we can interact with our world. We didn't evolve to understand software, so that 60% of our brain gets thrown out the window. When you look at the software code base, sort of on the right in this picture, it's strung together with a variety of interdependencies that are invisible, impossible to see, and when you think about the dimensionality of it, it's either non-dimensional or it might have 127 dimensions. Either way, it's very hard for human beings to reason about what is connected to what and to make inferences about the indirect and direct structural links between those components in the system. So understanding how it's built is extremely difficult. Now, when we look at Amadeus, we had Margaret Hamilton standing next to her stack of code for the Apollo 11. When we look at the volume of code in Amadeus today, it's 1,500 times the size of that code that was in the Apollo 11 machine. So if you printed out all of that code in the same way that we had in the picture, that stack of paper would stand 1.5 miles or 2.4 kilometers high. So the idea that any single human being could understand how Amadeus's system works is just laughable, and it's not because there's anything wrong with people at Amadeus. It just means that they're human beings. So one of the fundamental problems with modern engineering systems, systems that we create, is how, as a large enterprise, do you build a system that can function even though none of the developers that work on it really understand how it works, right? That's the challenge of modern engineering in our large-scale complex systems. And as a result, it shouldn't surprise us. These are some statistics on how successful large-scale projects are. It's very hard for all the reasons we just went through. This is a study that found that around 6 or 7% of large-scale projects were successful, if success is defined as, on time, within budget, and delivering the functionality they set out to deliver. 50% of the projects were challenged on at least one of those fronts, and around 40% of projects are just, failures. They are abandoned, started again from scratch, or just, left alone. Also, the projects that do make it into the real world, it seems like there's a daily news cycle where we learn about some new software failure out there. We've got Toyota brakes, and we've got the market crashing, not because of anything to do with the market, but because of computer glitches in the market. And I don't mean to pick on the stock market or Toyota. It's not them. It's all of us. It's everyone building large-scale software systems. We all run this risk. In 2013, Cambridge found that bugs cost the global economy $312 billion a year, right? And those are the bugs like this that are prominent, and also bugs that are small, and we all encounter many of them every day. So, Martin, you want to?
Yeah. So pretty much, with that in mind, with all the complexity and everything around, what we started to do with Server-Thread is acting on two axes. So the first one is, let's say, more oriented toward the software engineers and software leaders, which is helping them understand how their components work, how their platform is organized, so that when you take decisions on what to touch, where to refactor, you're actually confident and you have a good understanding of, let's say, the functioning of that thing as a whole. And the second axis is pretty much bridging the gap between the engineers and the business people. Mm-hmm. And it's allowing the business leaders to optimize the business outcomes by acting on the design quality an architecture of the product. So it's finding this common understanding between the engineers and the business leaders in order to get the biggest bang for your buck. And the key word here is communication and collaboration between those two separate entities of the enterprises.
Right. So we've talked a little bit about Amadeus. I'll tell you a little bit about Silverthread. I graduated from System Design and Management program back in 2008, went into the Engineering Systems Division PhD program, and then worked with Michael Davies at MIT and also Alan McCormack and Carlos Baldwin at Harvard. We did a lot of research looking at design quality in large-scale software systems and also software economic impact, right? So does design quality impact productivity, defect density, team morale, other things of economic interest? By how much? How can we quantify that? How can we reason about it? So we did a lot of research in that realm, and we founded Silverthread in 2013 to commercialize some of that work, but the research is ongoing. Our customers include people in government and defense, people doing due diligence, and people in large software enterprises like Amadeus. Focus actually is on design quality measures, right? How do you look at a complex software system and measure modularity, hierarchy, whether it's layered, APIs, whether it has reuse, or whether those things have all broken down and your system's turned into a giant furball, right? Also look at traditional code quality measures that have an economic impact that we can assess statistically, and also using software economics frameworks to help people make decisions. And these are the key questions that people often ask us, right? We're doing a lot of work with the Department of Defense right now, and often people, when they're trying to assess their 50-year-old system, will wonder how complex is it, right? Where are there tumors within it, right? Where has design quality broken down? Where will they struggle with a cloud transition or a platform transition or rehosting? Is architectural integrity inside a code base getting better or worse, right? How does it compare with others? Importantly, what's the difference between the system that I think I have, the system that's documented, and the system that's actually there? Because often there's a big difference. We see it all the time, 80% of the time, in fact, there's a difference. And then ultimately, how does this impact the organization, and what should we do about it? Where should we invest in high priority improvements? Should we refactor, redesign, or continue with maintenance? And how do we capture that business case so that people can come to some kind of agreement about it? So we've been building some tools, and we've been working using this platform with Amadeus to help people reason from an architectural standpoint, from a technology standpoint, as well as a business leader, say the perspective of a CFO. You want to make decisions about Gantt charts and project schedules and financial investments. Building platforms so that people like the Air Force can install this in their organizations and doing some consulting. So that's what we're doing here today. Now, these are the two projects that we've been working on with Amadeus. One we described about looking at the architecture of their complex system, their code base, and reasoning about its structure and helping them gain visibility into it from an engineering perspective. And then a second pilot is to reason about what's the ROI of different types of continuous improvement initiatives that they could fund, so that we can reason about whether they'll have a payoff, and use that to decide which ones to do. So let's jump into the first case, right? So this is about helping engineers understand design quality in their systems, right? So let's talk about what we mean by design quality. In a large-scale system, in software, we can take the system, we can partition it by using things like platforms, by making it modular, by having reuse, by structuring your system as a hierarchy of modules, and also thinking about the quality of individual components. And we don't build our software systems this way for the benefit of the computer. We do this for ourselves as human beings. Again, we just saw the picture of the size and scale of Amadeus's code base. If it was one big monolith, there's no way that a single human being with an IQ that's 100 would be able to cope with all of that complexity. And so we partition our system in these ways, and we structure them in these ways so that we can effectively treat that massive system as a collection of smaller ones that we can actually reason about. And so when you have good design quality in your system, developers can understand their code, or at least stand a chance. Teams can communicate effectively about that code, and the system can scale and evolve over time. For example, if you have a modular system, it means that I can swap individual components in and out when I don't like them, instead of having to throw away the entire system all at once and restart from scratch. So all of these properties are benefiting the humans in the organizations that develop their large-scale systems. Now, how do we reason about these properties that we care about? In hardware, it's a little easier to visualize, so we're going to start there, right? So our Apollo 11 lander, let's think about that as a Mr. Potato Head, right? Your Mr. Potato Head, you could think of as a platform, right? You take lots of different plugins and you plug them into Mr. Potato Head. You might have mouths or eyes, you might have ears, and as long as your platform is designed well, and then you can move those different parts into different places, and you can compose a different system out of those different plugins, right? So you can have Mr. Potato Heads that look very different from each other, all assembled from the same parts. Now, this relies on the platform developer creating a standard, which is that all of those holes are going to be the same shape and the same size. And if that standard gets violated, all of a sudden the options that you have in your Mr. Potato Head kind of go out the window, and you've got to start over again. Also, you could think of this as a hierarchical system, right? I've got a nose that plugs into the platform, which then plugs into the feet, right? And there's a top-down hierarchical control to it. We can also reason about modularity and reuse. An example is the Legos. These are composable, right? I can take Legos, and because there are standards around how big the nubs are, that they'll all be rectangular, I can plug them all together in a variety of different ways that allow me to make a race car or a house, for instance. And as long as everyone obeys those standards within those modular elements, then that's okay. But if modularity breaks down, if one team starts making nubs that are too big, or it's not quite rectangular, then again, all your options go away, and you've got a big rat's nest of a design. Also, reuse, right? If you design all your standards well, then I could take my Lego, take it off the car, and put it on the house, and it'll work just fine. Now, in software, it's harder to reason about these things. How do we think about design quality in code? Now, one of the natural ways to try to do that is to think in terms of networks, right? I've got entities within a code base, and I've got relationships between those entities. But the problem with drawing out a traditional network diagram is that it's really hard to interpret what they mean. So let me introduce some new notation for you. This is a design structure matrix notation for visualizing a network. Now, if you look in the upper left-hand side of this diagram, you see 4 software components. You see D depends on C, C depends on A, and C depends on B. In the lower left, we have indirect links. It shows that D depends on A indirectly through C. And that's really important because Team A could do something that breaks D through C, and it might not be recognized. It might not be recognized because those teams don't communicate with each other very often. So those bugs are going to be found late, they're going to be fixed late, and they're going to cost more. Now, if we look over on the right, we're seeing a square matrix notation that represents identical information to what you see on the left. If you see the dots at position C, A in the matrix, it means there's a dependency from C to A. Also, you see C, B, and you see D, C. Now, another thing that's important to note is that if you look at all these dots, they're all below the diagonal. I was able to draw this picture with all of those dots below the diagonal because this is a hierarchical system. It means that all of the arrows flow in one direction from top to bottom. And remember, hierarchy is one of those properties that we described as important from a design quality perspective. You want to have your system be a hierarchy of components. Let's go on to the next slide to describe a few more properties of design quality and how we can visualize it in this way. Now, what we've done here is we've blown out our system to look at many different components or modules within a system. If you arrange all of the files in this system so that all of the files are within the same subsystem positionally next to each other, for instance, if you look at all the files in B, they're next to each other, then what you see along the diagonal is you see a box where you see high degrees of internal cohesion within that box and low external coupling outside that box. This is one of the concepts that underpins modularity, right? So we can see it here in the modules that go across the diagonal. Also, reuse, right? If you look at A is a reusable component. If this is a C program, then that's printf, right? It is used by many other things, but it does not use many other things. Also, you see a control layer, F. That's main.c. In addition, we see that there are hierarchical dependencies between the components, but all those hierarchical dependencies are below the diagonal. That means that the circularity of dependencies is contained inside a module because that's very complex. You want it dealt with by an individual or a team. And interdependencies between those teams are hierarchical, so it's clear which teams depend upon which other teams. We don't want to be in a situation where teams depend upon each other circularly or their code depends on each other circularly, because you can actually get into an organizational deadlock. So let's move on and talk about why this matters. If you look at the picture on the left, we see the picture we just saw, the modular system. Unfortunately, when we scan code bases at Silverthread, 80% of the time we find that the system often does not look the way that developers describe it or what you see in the documentation. So with that, I'm going to hand it off to Martin, who's going to describe some of the pictures that we drew at Amadeus.
So this is, yeah, indeed the first thing we did. And you have to imagine that as a nice way to start the conversation with your developers, you have to imagine those pictures as a giant poster that you're going to put in the meeting room and say, hey guys, let's start talking about the architecture. So the cool thing about Amadeus and a lot of software companies, I have to say, is that we have a building system that has been built around build files where we basically explain what are the intended dependencies. So we say that when a component is built, it has to take this other component with it. So we had our intentional design, and that's what you see on the left. And then by analyzing the source code, we were able to display let's say the reality metrics that you see on the right. And that was interesting because the first thing that you can discuss with developers that now they see where the modules are and how they play out together. And how they depend on each other. So a funny thing, for example, is that for us, we had a business object model. And business object models, usually, they're pretty much like the A Dan was just describing. They're like a shared utility. Everyone is using it, and it does not depend on a lot of things because you want it to pretty much be a model. And we realized that it was actually depending on, I think, something like 11 other modules. That was a problem here. And those kind of design, they can show you very quickly at a glimpse where you have, let's say, misunderstanding between your intent and the reality. Another cool thing you can do with the DSMs is that you can use them so that they can show you risk areas and potential irregularities. So here we are back to an equal scale between components. And what Dan and his team did is that basically they took the matrix that you saw on the left before, and they checked whether the dependencies that were shown were legal ones or illegal ones. And all the red and yellow dots that you see are illegal dependencies. So here. And to reason with the developers, that was really interesting because, for example, we spotted this cyclic dependencies, which was about like wrong friendship or the developers cutting corner, and this is stuff you can easily do with C++. So that was we were able to spot just a few files, and we're not talking about hundreds of files. We're talking about, let's say, dozens of files that were breaking the modularity of the system. Also, we did a little survey with the developers, and it ended up that they were the least confident when they had to touch one part of the code. And actually, this part of the code was exactly what we spotted as a tightly coupled core, which basically means that you have a lot of interdependencies between modules, and that creates you a little core that is hard to debug, that is an area of high complexity, that pretty much is a risky area. So it was also enabling us to show to the managers why the developers were struggling more in that area of the code than in other area of the code. So it was supporting, let's say, the developer perception with more data.
Okay. So now we're going to talk about the second case that we did, the second pilot project. This is more around managerial decision making. Right. So we described design quality earlier. But we've done a lot of work to study its impact, right? Code quality can be measured, design quality can be measured, test quality can be measured. And this is the result of, this is a one-slide version of a dissertation. And what this found was that looking at a large enterprise and looking at which parts of a code base had good design quality and in which parts had it broken down, we found that in the parts with good design quality, developers were capable of producing 20,000 lines of code per year. Those same developers were only producing 8,000 lines of code per year when they worked in the part where design quality was challenged. In addition, developers, when they were working in the good parts, they were spending 4 days a week, or 80% of their time, working on features and only 1 day a week debugging. But when those developers were in the parts that were more challenged, they were spending 70% of their times on defense, debugging their code. So this represents an enormous economic impact for that organization, a lot of waste, a lot of overhead. These are some other examples. So we've done studies, and I'll skim past these, but we've done studies of safety critical systems and found that code had to be patched after a system went live a lot more often if it was in the part where design quality had degraded. We looked at security threats, found code bases that were being attacked regularly, and after they were refactored to improve design quality properties, it was easier to maintain and defend those systems. In addition, here's another commercial firm that went through a refactoring to improve design quality, and after a successful refactoring where our metrics showed the design quality had substantially improved, they were able to produce many more revenue generating products per unit time. So it gives you productivity, cost containment, safety, security, agility, and revenue. Design quality impacts a lot, and that's because ultimately design quality is what allows your developers to understand their code. It's what allows teams to communicate effectively about it, and it's what allows you to be able to swap parts in and out. It allows your system to be flexible, agile, and scale. One of the things that's important to talk about is that agile development methods, people talk about them a lot these days. There are the methods which receive probably 95% of the attention, but I think what's equally important is that you need an agile product. If your product is modular, then your product can support agility. If you have a process that's agile, but a monolithic furball of a product, you're just going to make crap faster. So it's important to deal with those as two sides of the same coin. So one kind of conundrum, we've talked a lot about how everyone understands these issues intuitively, and also how we've done a lot of research, and others have done research on the impact of code and design quality on the developers who work in it, and what that means for the importance of focusing on it, the importance of investing in it. Yet often quality efforts and refactoring efforts go unfunded. In fact, I think there's a systematic underinvestment in refactoring. So, do you want to talk about?
Yeah. So I think the thing is that new features, bug fixes, etc. They're pretty easy to. It's pretty easy from those to figure out what's the ROI. You have a return on investment that is easy to make and is that people are used to. On the other side, when it comes to investing in refactoring and everything, it's usually harder to make a case for what kind of investment I'm going to get. And usually it turns more into decisions or discussions about, let's say, different schools of architecture, different personalities, some people thinking that this is more efficient than this other thing, but it lacks of objective figures.
Yeah, and so an engineer will come to a manager and say, hey, I know that, let's pick an example. Toyota will pay us $2 million more next year if we implement this feature. And I know that we've got 10 bugs that customers are yelling about, but I don't want to do those things. I want to spend my time doing this third class of thing called making the code base more elegant, right? Now the manager's going to tell them to go pound sand if they hear that argument, but the engineer might actually be right? But the problem is there's no immediate market demand for that, and the ROI is extremely unclear, right? It's hard to connect the dots between the improved productivity and the reduced defect density, how that translates into future dollars, and how that impacts what you should spend today to make those investments. And because of that, there's probably a systematic underinvestment in refactoring efforts. So Martin and I think, now the studies that we went through, basically we're pulling data from these kinds of sources, right? I described a number of academic studies and commercial studies where we pulled data from source code, pulled data from continuous integration environments, pulled from version control and feature and bug tracking, and we got these raw metrics out. And then ultimately bubbled that up to get tables that we could run statistical models on. So we're looking at predictors like code quality, design quality, text quality, also a variety of controls that we would use about the system, and then use that to correlate with things that we actually care about, like defect density, developer productivity, morale, and so on, so that we can do those studies that we described earlier. I'm just going to fly past this. Here's an example statistical table. But ultimately, here's the question, right? How do you win over that CFO, right? How do you take this information that we can get out of these statistical models and actually win over a CFO to make them see the light and decide to invest in your continuous improvement effort?
Okay, so that's basically what we did in the second case study with Dan, and I have to say we're pretty lucky in Amadeus because we have CFOs that can listen to us. But let's take the example of one of, let's say, the various refactoring initiatives that we use to predict the ROI. So let's use the test coverage because I think it's going to speak to everyone. So test coverage, to remind everyone, is just you're writing software, it has lines of code, and pretty much you want to check if those lines of code are tested. And the test coverage is a measure to verify how much percentage of your lines of code are actually run through by a little piece of code that we call a unit test. So everyone pretty much agrees that the more unit tests you have and the more coverage you have, the less risk you're going to have. And if you find bugs early, they're going to be less costly to fix than a bug you find in production system, for example. Now, with everyone knowing that, it's not always obvious to get the money to actually fix that because of what we were talking before, because it's you might have other projects, you might have deadlines, you might be pressured by something else, and basically you never have a chance to improve your test coverage. So the first step is to build that story to say, hey, I'm gonna need this amount of time, but ultimately I can guarantee you that it's gonna pay off. And now, if you start addressing your CFO with a story like that, it's going to start listening to you. The second point is to actually get data to back up your story. So that's what Dan was saying, but basically in the Amadeus study, we extracted data from the source code, from the testing framework, so our continuous integration system, from the version control, for the issues, from the issue tracking, and we were able to create this data set of defect density, complexity of code, number of lines of code touched for the features versus number of lines of code touched for the defects, etc. And with that, we looked at the correlation between those different variables, and there was an obvious correlation an obvious negative correlation, for example, between the unit test coverage and the code created to fix bugs. Mm-hmm. So from that, we set up regressions and were able to build a prediction model.
So CFO should still be listening to you now. Right.
So we calibrate this model and we're doing a bunch of statistic stuff that probably your
CFO doesn't want to hear about all that, so we'll skip this step. Yeah.
And finally, you're going to use your prediction model to figure out now, if I'm pumping up my coverage to 90%, let's say, what do I expect in number of defects? And you're going to have a number of defects that normally should be fairly smaller than the one you have currently. And if you subtract it to the one you have currently, then you're going to get the gain in terms of defects. And here, probably your CFO starts to listening more and more, yeah, because you're actually reducing the risk. But you've not talked about money.
Not almost all the way there. Right.
So to talk about money, you need to build cost models. So, and those are not gonna say they're easy to do, but you have data to do it. you know the productivity of your engineers, you know how much they cost per year, you know how much lines you're going to have to touch to improve this code coverage, and from them you can build an estimated cost of what it's going to take to reach this 90% of code coverage. On the other hand, you also know the productivity of your developers when they fix defect. You know what are the, let's say, indirect cost of a defect in terms of your customer service and all that kind of stuff. And from that, you can you can build a cost model about what a defect costs. Now, if you compare the two of them, you start having a return on investment.
Right. So now your CFO might actually like you. And if we go on to the next slide, this is the key to getting them to even respect you, right? So, we can use finance equations, net present value equations, to compare the future value streams that you derive from that productivity increase and the defect density decrease that you'll get over time as a result of this refactoring effort today, right? So we've got to compare the present value of this future value stream against the cost of doing a refactoring now, and then use these ROI equations to compute ROI and other things like time to pay off, right? So in this example, in this toy example, ROI was 279%, and that may be a hurdle or not for an organization, but the important point here is that CFOs every day make investments. They decide whether they're going to build a new plant or hire new people or do all variety of things based on projections of ROI. And so if you can do this kind of modeling, all of a sudden your refactoring effort or your continuous improvement effort can be compared side by side with those other things that you invest in. Now you might do some modeling, sensitivity analysis. You might think through what are different reasonable assumptions. There might be some variance in here. But at the end of the day, we're trying to put this in a language that they can understand and use to compare and trade off how money should be spent so that that money can be invested wisely. Now, it should be noted, that we actually did a few of these projects at Amadeus. We're not going to show you the numbers that came out, but we looked at test coverage. We looked at things like McCabe's cyclomatic complexity reductions and other kinds of initiatives that could be kicked off that would represent investments in continuous improvement of a code base to optimize long-term considerations versus short-term considerations. So I don't know, Martin, if you want to talk about.
Yeah, I think I'm gonna to conclude as Dan say. Now you're comparing apple to apple, and that's way easier for everyone to have a discussion.
No.
So to conclude a little bit on the feedback and the lesson learned that we had in Amadeus and how this can play out in your company as well. So first of all, we presented those analyses to a different set of people. So first, developers, and it was obvious that it sparked architecture discussions. It helped them to figure out why they were struggling in that part of the software and thriving in another one. It also we also presented it to their technology leaders, and that is enabling a discussion between the developers and their leaders to understand, hey, is that development riskier than the one we did before? Can I be confident on the outcome of that thing? Actually, Mr. Whomever is not a bad developer, it's just that he's developing in an area of the code that is a little bit touchier than the rest. And finally, for the executives, so we presented those spreadsheets to, let's say, senior level management in Amadeus, and the big thing that came out of it is that people were actually pretty impressed with the ROI. they didn't necessarily expect it to be so high. But for the first time, they were able to reason together between, I don't know, your CFO and your CTO and your engineers. You're suddenly all talking the same language, which is ultimately money. Finally, and that's what we intend to do in Amadeus in the future, is using this kind of analysis as a cycle, not as a one-shot project, but basically using this approach as a way to continuously improve. And the good thing about data and data-driven decisions is that the more you do it, the better you're going to do it. So the more we have this refactoring initiatives, the more we're going to improve our cost models. The more we're going to learn other things. The more data we pull, the more correlations and the more prediction models we're going to be able to make. And ultimately, this is like a virtuous circle of refactoring and of controlled refactoring, which is going to be answering what Rashesh wanted in the first place, which is pretty much being more agile, going to the cloud, and making sure that every decision we take is backed from data.
Great. So I think with that, we're ready to take questions.
Okay, so this is Lois, everyone, again, and I am going to hand the Q&A over to Rashesh. We have many questions. We'll get to as many as we can within the next 10 minutes. Would you folks be interested in staying another 5 or 10 minutes to answer more questions, or do you need to?
Absolutely.
Yeah, okay,
Yes.
great.
Absolutely. Thank you.
So,
Yeah, we'll try to get through as many questions as we can in the time that we have, of course.
okay, it's all yours.
All right, so let me go through some of the questions we have, and then we'll just decide
Yeah.
who's best positioned to answer the question. So I'm just going to go in chronological order. There's a couple of questions up front that talk about how many software bugs do we generate per year, how many do we resolve, what percentage of code do we no longer execute. I mean, the intent of this webinar is to essentially demonstrate how we are using what we consider fairly advanced thinking around system design, along with Dan and his company and the researchers here at MIT and their experience with very large distributed systems. So I'm going to stay away from actually talking about specifics around Amadeus code base. I can talk about, in terms of the percentage of code base that we no longer execute, which is frankly not that much. And then hopefully, Dan, you saw evidence of this even in the pilot studies that we did. And the simple reason for that is, we are moving to a very microservices based architecture. And the reason we even have a project of this kind is to essentially understand, what parts of our code can benefit the most when we refactor. So which ones can we actually essentially break up into very, very smaller executable pieces of code that can be very easily invoked. And this is part of the larger strategy to move to a cloud computing environment, where we essentially want to abstract the software that runs from the underlying infrastructure that runs it. And to do that, you really need to have very efficient code in terms of both the execution of the code, in terms of the timing and the efficiency, but also the quality and also the fact that it's modular and can be easily invoked through APIs. So in our case, we've gone through a fairly long and very detailed process as we moved away from the older proprietary kind of closed mainframe systems, because we are running an open systems, Linux-based shop at this point. It was very essential that we went through and looked at our entire code base, and I'm happy that it's all behind us. So when I look at our current quality of our current code, I'd say very, very small percentage of that is in that category of no longer being executed. But there are some other interesting questions, and I'll turn them over to the two of you, Dan and Martin. There is a question around what's involved to create those DSM matrices for software code. So maybe Dan.
Sure. So we have a product where we can extract dependencies and entities from a code base. So no matter what language you're dealing with, every code base can be thought of as entities, be they classes, files, functions, methods, and so on, or relationships. This one calls that one, or this one subclasses from that one, or this file contains that thing. And given basically technology that's the front end of a compiler or an interpreter, you can pull those kinds of things out. extract them into a matrix, a sparse matrix, or into some kind of network algorithm, and then go from there. So we've got that inside our product, and we can certainly scan your code if you're interested.
I think also there are a couple of papers that you made, you and Alan McCormack especially, to explain how you can put a network into a DSM and how you can do it with your code.
Yeah.
What the complex part being how you extract the dependencies from the code.
Yeah.
So, Martin, maybe this question would be interesting for you to address, and that one's around, in the pilot, in the study, we've generally focused on the source code, the version control, the feature bug tracking system. I mean, these were our primary data sources. What other kind of data sources do you think would make sense to refine the economic analysis that we did, both the real one that we did and the hypothetical example that you guys presented here today?
So I think in let's say the specific case of Amadeus, because we're a service-oriented architecture, so software is one thing. You also have the let's say runtime dependencies between components. So that would be another source of data that would be let's say very, very useful to have. Let's say to have another perspective on dependencies and components. There would be, I don't know, data extracted from the logs, data extracted from if you have anything like an enterprise bus or a service integrator or whatever. Other source of data that you could think of to enrich let's say the cost models might be around mining a little bit more than the incident tracking system, and this is something I had in mind for the future. But it's also, I mean, when we speak about defects, it's also hard to get an idea of what's the exact cost of a defect, because it's involving so many people in the enterprise. So you can also use probably natural language processing techniques and stuff like that to mine from. You probably all have IMs or email threads whenever a problem happens, or you use your regular Bugzilla or whatever to find out what are the interactions between people. And yes, that's pretty much it. Then after you can also refine probably the models and not necessarily talking about lines of code, but more about let's say what value your software is producing, which is also like the tendencies that a lot of companies are using. But then it means that you have to understand exactly the value of each part of your software. I don't know, Dan, if you have like other source of data that you've used also with other companies.
I mean, there's all sorts of things you can use. You can use social network information within the organization and figure out what's the relationship between the social structure or the organizational structure and the code base. There's all sorts of different things. You could even use that kind of information to figure out what the floor plan of your company should be within the building to optimize the communication channels, right? So there's all a variety of things.
Data driven all the way.
Yeah, absolutely. So.
So just to stay with that theme for a couple more minutes, one of the questions is, on the software economics, the cost models are pretty basic. How could they improve? I think, Dan, you just gave an example of how we could improve it, right? So the traditional cost models have always been, your finance-driven spreadsheets, and the more data inputs you have, the more kind of modality you can put into those models. I think you just have better models.
First of all, you should know that what we presented wasn't the actual product. It was simplified and obfuscated to protect maybe the innocent.
Thank you.
And so we did a fair amount more work than what was shown in the presentation today. So was the question about the finance models or the cost models?
Right. I mean, the question, the person that asked the question was saying the cost models are pretty basic. How could you actually improve? And I think hopefully we just demonstrated how we can actually improve them.
Yeah. So what we've done here and in other places is, you've got regressions that of all different kinds that allow you to build models around how productive are people when they are fixing bugs? How productive are they when they are implementing features? How many bugs are there? under different conditions, how many of those bugs are critical or have different levels of severity, or maybe have a customer impact, because if there's a customer impact, then there's not just the cost of fixing the bug, but then there's the downstream impact. And in our tools, we have little dials you can turn. You know, if it's a nuclear plant control code base, then you're going to have that risk go sky high. And if it's a cell phone app, it's going to go down to nothing. You can also think about, you know, a variety of other things like, you know, what's the value of optionality in your architecture, and how do you, you know, place a financial value on that flexibility. So there are a variety of things that you could do to build out a model of the relationship between design quality, code quality, and software economics. But ultimately, you're going to want to kind of hone that in so that it's appropriate minimally for the types of questions that you want to ask. So we've done that in a variety of contexts. And maybe you appreciate that the one we presented today is sort of touching the tip of the iceberg.
Thanks. There's a series of questions. I'm going to try and see if I can synthesize them to the one or two questions, and that's around testing. And there's a philosophical statement by, I think this is Edgar Dijkstra, that talked about, you know, testing showing the presence, not the absence of bugs. There's also a related question around the relationship between bugs and vulnerability to cyber actions, both internal as well as external, intentional or accidental. You know, and maybe also somewhat related is in the cloud, how do you know who else is using your code? So let me maybe take a first shot at some of these questions, and you guys should feel free to jump in as appropriate. So a big focus of the analysis we presented and the study we presented was actually coming back to the thesis of this webinar, was to find out how we can examine the modularity in our systems, how we can use, you know, data-driven, you know, objective methodologies, you know, what I'd call pretty cutting-edge methodologies out of the research institutions, you know, like MIT and the work that Dan and his team are doing. How can we look at it fairly objectively and say, look, what part of our code, you know, will best benefit from any refactoring that we do, or any work we put into it, and to make that decision on the basis of data and on the basis of actual code, not, as Matan said earlier, not declared intentions, but what does the code actually look like? And that, you know, the data actually tells you this is the biggest bang for your buck, if I were to translate that into layman terms. Things around bugs, or, you know, what is the impact on security? I mean, I think that's a whole different area of discussion. It's unrelated to what we presented here or the study, and the pilots we did here. But any thoughts?
Yeah, I mean, cyber, I'd say ultimately, when people can't understand the code that they're working in, they make more mistakes. And that means that they make more defects. And one class of defect is the introduction of a vulnerability. Also, modularity, the other thing that it gives you from a security perspective is that if you have a modular system, it has a smaller attack surface area. But we haven't gone too far into that, and that's sort of a topic for another day. There were some other questions around bugs, like
I think one was a more philosophical statement. Do you agree with it or not? So,
the absence of bugs, proving the absence, or the...
I mean, no, I completely agree that testing is it's showing that some bugs do not happen. Does not mean that you don't have any bugs, but I think it has been fairly shown that if you don't test, you're in trouble.
Yeah.
It's not, I mean, you're going to need to do other things than just testing. And this is also what plays out to what Dan said, is that you need to understand what you're doing. I think that's the big thing about architecture, is that it's not something that just the architects need to care about. It's something
that's actually a very good point, which is, you know, a lot of classical technology groups, you know, there's people that have the title of a software architect, and really what we're looking at is, you know, architecture should be something, even if you're a developer and your job is not to be a software architect. I think understanding that architecture and understanding kind of the broader context of where your code fits into is absolutely important and critical. So since we are over time, maybe I'll just sneak in one last question, and I think this question probably ties a lot of things together to make it very relevant.
And one thing I'd throw out is that you see our email addresses on this screen right here, and I'm sure they'll be distributed. I know that I would be very happy to follow up with you via email to answer any other questions that you have, even though we can't hit everything today.
Yeah, so the question, and we'll just wrap on this one, is, how can Amadeus help to drive innovation? Is it related to distributed or open innovation? Can it be used by subject matter experts and startups? And I think this actually speaks to, at least in our case, how moving to a more distributed systems, moving to open systems, moving to microservices, all the things we've touched on here briefly, how that benefits innovation in the industry. Because part of what we can do is, we can open up, and we do this, we have a developer program where we have a set of published APIs, and anyone can essentially register, sign up for it. And you have access to some of the transactions that we support in the travel industry, that you may have a very creative idea, but you really don't have, as a startup, for example, or as a subject matter expert, you don't have the access to the entire ecosystem of travel suppliers and partners that we do have. But you can work with us, and we can give you a set of APIs that can, for example, let you look at flight availability, can let you look at hotels. And we've been working with a couple of hundred startups just here in North America, and even more globally, where companies have been able to access this set of APIs and really come up with very, very creative ideas and business models, which ultimately goes to improve the life of us as a traveler. And because innovation is everywhere. And so for our part, being kind of one of the predominant platforms in the travel industry, this is the way for us to also foster innovation, not just internal and within the 5,000 and more developers and engineers that we have in our company, but also in the industry. So with that, we are fashionably 6 minutes over time. Lois, thank you very much. Dan and Martin, thank you. Thank you again. And as you said, our emails are there, so feel free to reach out with further questions, or if you have.
And if you have questions typed into the screen, I will respond to them, certainly.
Okay, thank you very much. Great webinar. Thank you all for attending. This is the last webinar for this semester. We'll be resuming in September. But in the meantime, please visit our website where you can see a listing of over 100 webinars that are available on demand on topics like these and very far-flung topics you wouldn't even expect, all tied together by systems thinking. Thank you again, and have a great day.